Okay, let's start again. This section is triple integrals using cylindrical coordinate system. Should be on the much easier side because we already did the difficult part in the previous section, 15.7. Okay, let's take a look. So number 20. Number 20, evaluate triple integrals over solid E of x dv, where dE enclosed by the plane C equals to 0 and C equals x plus y plus 5, and by cylinders x squared plus y squared equals to 4, x squared plus y squared equals to 9. So let me imagine this first. On the ground, when C equals to 0, that will be when C equals to 0, that's hard. Let's C equals to x, y, C equals to 5. Let's say x equals to, so it looks like the plane is actually sticking out, It looks like this later on. I don't have enough space. So the plane will be sticking out like this in 3 dimension. Okay, yeah, in 3 dimension though. You know what? I think I better do it this way. Let me start from the xy plane. On the xy plane, that will be a donut between radius 2 to radius 3. I think that's easier to see it that way. Okay, this guy here will give us this, and then it is bounded below by C equals to 0, bounded above by C equals to x plus y plus 5. This is 2, this is 3, so our triple integral now will be from 0 to 2 pi, the radius from 2 to 3, from z equals to 0 to c equals to x plus y plus 5, but x is r cosine theta plus r sine theta plus 5 of x. X is r cosine theta r dc dr d theta. Okay, again, this is my x. Oh, don't use that same color. This is my x. This is my dv. My dv actually consists of dz dA, right? But my dc dA is dc r dr d theta. Okay, now this will be integral from 0 to 2 pi, integral from 2 to 3, r squared cosine theta times r cosine theta plus r sine theta plus 5 dr d theta. How to integrate this best? This is r cubed cosine squared theta plus r squared cosine theta sine theta plus 5r squared cosine theta dr d theta. Notice that each of them actually separable, right? Yeah, each of them is actually separable. So I can integrate it this way. For the first term, I get integral from 0 to 2 pi of cosine squared theta d theta integral 2 to 3 of r cubed dr plus, that's for the first term. Second term, integral from 0 to 2 pi of cosine theta sine theta d theta integral from 2 to 3 of r squared dr plus the last integral is 5 integral from 0 to 2 pi of cosine theta d theta integral from 2 to 3 of r squared dr. What I want to say is this goes to 0, this also goes to 0. To see it better, you may want to rewrite this part here as integral of 1/2 0 to 2 pi of sine 2 theta. Okay, that will give you 0. Now, so basically we will get this part here, that's integral from 0 to 2 pi of 1 plus cosine 2 theta over 2 d theta times 1/4 3 to the 4th minus 2 to the 4th. Okay, but again, you will see this part goes to 0. Okay, so we get only 1/2 times 2 pi times 1/4 times 81 minus 16. So that's pi over 4 times what? 65? Yeah, 65 pi over 4. Okay, remember I told you that the integral of cosine from 0 to 2 pi, 0 to pi, or even 0 to pi over 2, it will be nice if you can memorize them. Okay, so notice that the period for cosine 2 pi, the period is pi, right? So, so if we take a look what the graph look like from 0 to 2 pi, it already have 2 cycles, and the area actually cancels each other. The area here cancels the area here. The area here cancels the area here. So basically, all of them will become 0. That's one of the way we do the interpretation. You can also just do it using calculus. You integrate that and see that the endpoints both becomes 1, right? Okay, now that's the faster way to do that. So how to say this? What makes it easier is we use cylindrical. Okay, basically the xy plane becomes polar, right? And then using we benefit from the fact that we do integration from 0 to 2 pi. Okay, that's for number 20. Let's go on to number 21. Evaluate triple integral over solid E of x squared dv, where the solid E is the solid lies within the cylinder, x squared plus y squared equals to 1, above xy plane and below the cone. If I try to sketch that, it's below the cone, but inside the cylinder. Okay, so the double integral in the outer two integrals set from 0 to 2 pi, 0 to 1, right? And then as for the z, that will be from z equals to 0 to c equals to c equals to square root of 4, that's 2 square root of x squared plus y squared, which is 2r. X squared is r squared cosine squared theta dc r dr d theta. I think you can integrate it yourself already, right? Okay, so this becomes integral from 0 to 2 pi, integral from 0 to 1 of r cubed cosine square theta times 2r dr d theta. The domain is a rectangle, quote unquote, because all constants, right? And then the integrand are separable. So we can do integral from 0 to 2 pi of cosine square theta d theta, integral from 0 to 1 of 2r to the 4th dr. The first integral is, well, I hope you remember. That's all. I just work it out. So integral from 0 to 2 pi of 1 plus cosine 2 theta over 2 d theta. And then the second integral, the second factor will be 2, just 2/5. Right? So this will be 1/2 times 2 pi times 2/5. That's 2 pi over 5. Why? Because this part will give you 0. Dang, that's really fast, huh? That's really fast. Okay, that's for number 21. We did 22 in my lecture videos. Let me move on. How about number 23? I don't really do odd numbers, but because I think I want to do more examples, let me just do more. And number 23, find the volume of the solid. Find the volume of the solid. Let me scroll it up a little bit. Okay, number 23. Number 23. That is enclosed by cone z equals to square root of x squared plus y squared, which is r, right? And sphere, z equals to square root of 2 minus x squared minus y squared, which is square root of 2 minus r squared. The cone looks like this, and you have the sphere. So it looks like an ice cream thingy, right? Okay, where do they intersect? First of all, they intersect at c equals to r equals to square root of 2 minus r squared. Square both sides. So 2r squared equals to 2, so r equals to plus minus 1, but because we use the radius 1. Okay, so the domain will be a disk with radius 1. Okay, so the volume is double integral over the disk with radius 1. And then of that cone, we start from r and goes out from square root of 2 minus r squared dv, right? So this will be r dc dr d theta. That's 2 pi integral from 0 to 1 of r times 2 square root of 2 minus r squared minus r dr. I split them. And then for the first integral, I will use substitution. U equals to 2 minus r squared. Du will be negative 2r dr. U at 0 is 2. U at 1 is 1. So this is 2 pi integral from 2 to 1 of u to the power of 1/2 du over -2 minus the second part is easy, that's just 1/3. Let me continue here. So this is equals to 2 pi integral from 1 to 2 divided by 2 of u to the power of 1/2 du minus 2 pi over 3 to okay, this will be 2/3. You know what? Let me write it properly first. This will be u to the power of 3/2 from 1 to 2. So this will be 2 pi over 3, 2 radical 2 minus 1. Altogether, that will be 2 pi over 3 minus 2 pi over 3 again, right? So that's minus another 1, that's 2 radical 2 minus 2. I can factor the 2 out. That's radical 2 minus 1. Okay, that's for number 23. I think number 28 will be the last one. At the same time, basically, you will see there's nothing really new here, except that when we project it on XY plane, we make it into polar. Okay, number 28. Find the mass of the ball B. So this is a ball with radius A, with density, if the density at any point is proportional to the distance from z-axis. The distance from z-axis is square root of x squared plus y squared. So in polar, this is kr. Okay, now remember there's a ball, okay, with the radius a on xy plane. On xy plane, this is what we have. Okay, so the mass of that ball B will be triple integral 0 to 2 pi 0 to a. Now the z component from square root negative square root of a squared minus I solve for z minus r squared to square root of a squared minus r squared kr dc r dr d theta. So that's independent of theta. So let me just get 2 pi integral from 0 to a. I pull the k out. We have r squared inside, and then 2 square root of a squared minus r squared dr. Am I missing anything? This guy will give me this. This guy will give me this. Okay, and then what else? This guy will give me this r squared dr. So I don't miss anything now, huh? I don't miss anything. Okay, so the thing is I have that r squared. I don't like that. How do we do this? Oh, seems like I cannot avoid doing trig substitution, huh? So let r equals to, let's say, a sine theta. Don't use sine theta. You may confuse with that theta. Sine alpha then. So dr equals to a cosine alpha d alpha. Okay. When r equals to 0, the alpha will be 0. When r equals to a, the alpha will be pi over 2. So we get 2 pi k integral from 0 to pi over 2 a squared sine squared alpha times, that's a cosine alpha times a cosine alpha d alpha mu. So that's 2a to the 4th k pi k integral from 0 to pi over 2 sine squared alpha cosine squared alpha d alpha. Now remember that sine 2 alpha equals to 2 sine alpha cosine alpha. So sine alpha cosine alpha can be substituted by sine 2 alpha over 2. Right? When we square that, it becomes sine squared 2 alpha over 4. Okay, so that's a to the 4th pi k over 2, like 2 divided by 4 becomes 1/2, integral from 0 to pi over 2 of sine squared 2 alpha d alpha. And then from here I go further, do power reduction. Okay, so that's a to the 4 pi k over 2 integral from 0 to pi over 2 1 minus cosine 4 alpha over 2 d alpha. You will see this goes to 0. So we get a to the 4th pi k over 2 times 1/2 times pi over 2. That's a to the 4th pi k, pi squared k over 8. No, I don't like that pi, another pi. But maybe that's the case. So be it. That is for this 15.8.